Hello, my name is Andrew Liu, and today we'll be proving proof 8.4, which is Taylor's remainder theorem. And let's let f be a function defined on the open interval a to b, where 0 is in between a to b, and f to the nth derivative also exists on the open interval a to b. So let's define the remainder as r of sub n of x equal to the function of x minus this summation right here that counts from 0 to n minus 1, basically showing that the remainder is the difference between this function and this finite sum right here. So let's prove that for all x not equal to 0 in the interval a to b, there exists a y such that y is between 0 and x, where r sub n of x equals to f to the nth derivative times f to the nth derivative of y over n factorial times x to the n. And that looks a little bit complicated right now, so we're going to rewrite that. So we're going to fix x not equal to 0, and we're going to choose a value of m such that we can rewrite this function here to be equal to the same summation right there, k equals 0 of n minus 1, and f is to the kth derivative over 0, like that. And then we're going to add on the remainder, but this time we're going to replace f to the nth derivative of y with m, so that your remainder is m over m times x to the n over n factorial. So now we're going to try to show, or we're going to want to show, that there exists a value of y in the range of 0 to x, such that f to the nth derivative of y equals m. Basically, we can put this right back in there and we'll get the remainder that we see right there. So the first thing we're going to do to prove this is we're going to set a function g of t, to be equal to f of t. So we're going to take this, but in terms of t, and we're going to subtract f of t from it again. So this is still from k equals 0 to n minus 1 of f to the kth derivative at the center 0. And instead of x here, we're going to put t, and we're going to add in this remainder here. So instead of an x, we're putting t, so m times t to the n over n factorial. And the last thing we're going to do is we're going to subtract the whole function f of t again. So we're going to see that if you put in any number in here for t, then it's just going to become 0, because you essentially have f of t minus f of t. So we can choose an x. So let's choose x1 that's a part of the interval 0 to x, such that g prime of x1 equals 0. What we're doing here is we're going to implement Rolle's theorem, because as we'll see at these endpoints 0 to x, g0 equals f0 minus f0, which is equals 0. And we'll also see that g of x equals f of x minus f of x, which is equal to 0. So that means because the endpoints are equal to each other, we'll be able to find a point where the slope in there is also equal to 0. Hence, in this case, g prime of x1 equals 0. So by Rolle's theorem. Okay. So after that, we can set up for Rolle's theorem again. If we choose a value of x sub 2, that's a part of this interval 0 to x sub 1, where g double prime of x sub 2 equals 0. And this is because we'll see that g prime of 0 equals f prime of 0 minus f prime of 0, where we're just taking the derivative of this and the derivative of that, the same thing. That equals 0. And then we can see again that g prime of x1 is 0 right there. So then we know that the endpoints of the function g prime are both equal to each other. So it sets us up for our next step, where we can choose an x sub 3 as part of the interval 0 to x sub 2, and this interval keeps on getting smaller, such that g prime of x sub 3 equals 0. And that's pretty similar here, where g double prime of 0 equals f double prime of 0 minus f double prime of 0 on this end of the function g double prime. And then we'll also show that g double prime of x2 on this end equals 0 as well from back here. Okay, so we can actually do this many times, an infinite time, up to n, such that we have an x sub n that's a part of the interval 0 to x sub n minus 1, where g to the nth derivative of x sub n equals 0. And that's going to become important in just a sec to help us prove what we're trying to show right here. So first thing we can do after this is we're going to take the derivative to the nth derivative of this function g of n, because we're trying to get something like that. So g to the nth derivative of t is equal to, this whole first summation is going to become 0, because this only goes from the counting 0 to n minus 1, so this function only goes up to the n minus 1th derivative. So if we take the nth derivative of that, we get 0. Okay? This right here is going to become just m, because we're taking the nth derivative of t to the n right there, so that's going to become m. And right here, we're just going to subtract f to the nth derivative of t. Okay? So based off what we have right here, g to the nth derivative of x sub n equals 0, let's plug in x sub n for t right there. So g to the nth derivative of x sub n equals 0 plus m minus f to the nth derivative of x sub n. Okay, and remember that equals 0 here, so we'll say that 0 equals m, we'll just take that 0 out there, m minus f to the nth derivative of x sub n, which also means that m is equal to f to nth derivative of x sub n. And that looks really similar to what we're trying to show here, where f to the nth derivative of y equals m, but right here we have x sub n. We can make it look like that because this value of x sub n is in the interval 0 to x sub n minus 1, which is actually smaller than 0 to x. So then we could say that there exists a y such that it's in the interval 0 to x, where f of n sub y equals m. All right. Now, to finish it off, if we put this right in there, we can show that r sub n of x is equal to f to the nth derivative of y, like what we have here, over n factorial times x to the n. And that's exactly what we were trying to prove earlier. So there we go. We have proved the Taylor's remainder theorem.